going to start off this section by talking about mass. Now, we know that the force applied to an object is the mass times acceleration. We just divide by acceleration. We divide both sides by A to get M alone. Like I said, both sides. We learned that the mass is nothing more than F over A. The mass of an object is the force divided by the acceleration. In different planets, the acceleration is different, so the mass would be different. Okay, so suppose at sea level, an object weighs 1 pound. Weighs exactly 1 pound. How much is the mass? Well, we know the mass is the force divided by the acceleration. The force is the weight. 1 pound. And pound. We're not in the metric system. In the English system, acceleration is 32 feet per second squared. Well, it turns out that pounds divided by feet per second squared is kilometers. No, actually it's a slug, excuse me. So it's 1 over 32 slugs. And if you do that division, which I worked out actually, is 0.03125 slug. That's how much the 1 pound, that's the mass of the 1 pound object. So it's just F over A. You want the mass, it's F over A. What if I told you that at sea level, an object doesn't weigh 1 pound, but rather it weighs 9.8 newtons? And let's do this problem to the left. Let's do it over here. We know the force is equal to the mass times acceleration. And the mass is 9.8 newtons. And acceleration, newtons is in metric. Acceleration should be in metric. It's 9.8 feet per second squared, except it's meters, not feet, excuse me. Well, you divide those two numbers, you get 1. And newtons divided by meters per second squared happens to be kilogram. So, of course, what we did was wrong on the top, sorry. Force is M times A. I meant to say this formula over here. The mass is equal to the force over the acceleration. That's the force, and that's the acceleration. The mass is 1 kilogram. So it's just force divided by acceleration. Make sure the units are right, and you won't have trouble with that. The next topic is moments. The next topic is a moment. Suppose, so let's label it. Suppose you have a seesaw. It has a fulcrum and you put some weight here. Maybe you put 50 kilograms, excuse me. And over here, you put slightly less, 30 kgs. And the distance from the fulcrum to the 30 kg object is 5 meters. And suppose the other distance is only 3 meters. The question is this in equilibrium? That is, let me draw it a little bit straighter. Would the seesaw be level? Would the seesaw be level? That's the question. And it is if what's going on in the left and what's going on to the right are somewhat equal. They somewhat equal. On the left, you have 50 kgs times a distance of 3 meters. If you think about something, suppose you have this pole. Have a pole. And maybe it weighs 5 pounds. Well, if you picked it up in the middle, you wouldn't have any trouble. But if you picked it up here, it might be a little bit harder. If you pick it up at the end, if you try to grip it right there, it seems like it weighs a bit more. It seems like it weighs a bit more. Okay? As you deviate from, say, the center, it seems to weigh more and more. And I'm assuming that the weight is evenly distributed in this rod. It's evenly distributed. That is, it's not heavier on one end than another. If you think I'm wrong, pick something that weighs 5, 10 pounds, and in the middle, anywhere in the middle, you can easily pick it up. But try lifting it at the end. It seems a bit heavier. So the distance matters. Now, where you're picking it up at, in our example here, is in the center at the fulcrum. How much force is this applying right at the center? And the answer is 50 kgs times 3m. Well, 50 times 3 is 150, and whatever kg times m is, it's kg times m. Well, on the right side, you have 30 kgs times 5m. Well, 30 times 5 is 150 kg times m. These are equal. These are equal. This system, this diagram, is said to be in equilibrium. Okay, and the board, the seesaw board, will stay horizontal. If you add more weight to the 30 kgs, it would go down. Or, if you moved it closer, it would go down. Notice we multiplied the mass by the distance. That's what moments is all about. The moment is add up all the distances times the masses. Turns out that the moments is equal to the symbol m0. That didn't write, so let's write it again. It is equal to, or denoted by the symbol m0. And it means add up a lot of things. add up the m times the x's. mi times xi. As I goes from 1 to whatever. For example, you have this board, this is the board, and you have the famous fulcrum. And you put some objects. You put this object, it has a mass of m1, another object, a mass of m2, a third object, say, a mass of m3, a fourth object, mass of m4, and the last one, many more in between m4 and the last one we call m sub n, the nth mass. And you should think of this line that I drew as an axis, and you think of the fulcrum being at 0. So this is x1, maybe it's -3, because if you're to the left is 0, you're negative. This is a distance x2, x sub 3, x sub 4, all the way up to x sub n. Now, the moment is very easy to calculate. You multiply the mass by the position. It's at x sub 1. It's m1 x1 plus the mass times the distance from the fulcrum, x2, plus m3 times x3, m3 x3, and so on, including m4 times x4, all the way up to mn times xn. You may say, well, you didn't write m4 x4. Sure it is. It's in there. I also didn't write m5 x5. It's in there. And if you notice, a lot of these things look the same. For example, they all have an m and an x, an m and an x, an m and an x, mx. And we're adding them. So it's the summation of mx. And what changes are these subscripts. So let's call them I. First they're 1, and then they're 2, and then they're 3, all the way up to n. So we say the summation as I goes from 1 to n. Just like I said up here. And when you do this calculation, you find out what's called the moment. You find out what the moment is. Let's work an example out. And we'll calculate the moment. That will be the example. You have some axis, call it the x-axis. Call it any name you like. Okay, there it is. And here's the fulcrum. Doesn't have to be at the center. And you have some weight here, 20 kgs, and another weight here, a little bit less, 7 kgs. And you have this very big mass, 45 kgs, and along here you have a little one, 2 kgs. And this is at -3, or -3, -2, -1, 0. I'll call this 1 and 2 and 3 and 4. So we have our mass at -3. We have one at -1. We have our 40 kg mass at 2 and one at 4. So the moment m sub 0 is you multiply the x by the mass. It's -3 times 20 plus -1 times 17 plus 2 times 45 plus 4 times 2. And you get what you get. Negative 60 plus a negative 17 plus 90 plus 8. Well, 90 minus 60 is 30. Plus 8 more is 38. Let's not forget to add the negative 17. That is minus 17. 3 minus 1 is 2. 8 minus 1 is 7. So it turns out that m sub 0, the moment, is 21. The moment is 21. Since it's not 0, it's not in equilibrium. If it were 0, we would say, yep, it's equilibrium. Now, how would you put this, how would you make this equilibrium? And the answer is you would move the fulcrum. Let's say, for argument's sake, we move this fulcrum. Let me dot it. We move this fulcrum to the left. We now put it at 2, for example. We now put it at 2. Okay. We now put it at 2. That is the same. So now, let me use a different color. So now, that's 0 and negative 1 and 1 and 2 and 3 and 4 and 5 and 6. That would be the numbers on the horizontal line, on this line. Because the fulcrum, we always call that position 0. Now, let's see what happened. It looks as if we could have just moved, instead of moving the fulcrum, so let me erase this down here, and we notice something. Instead of moving the fulcrum, we could have moved the masses. In other words, we could have kept the fulcrum right at 0. And we'll move the first mass 1, 2 to the right. That puts it at 1. That would be the 7 kgs. And the 45, we'll move it 2 to the right, which it used to be at 2, now it'll be at 4, just like we wanted to get it at. It's the same as moving the fulcrum from here to there. Instead of moving the fulcrum 2 units to the left, and after all, if you go from 0 to negative 2, you went 2 places to the left. Instead of doing that, you can move the masses 2 units to the right. Instead of being at 2, move it to 4. Instead of this being at 4, move it to 6. That is, we're going to just do a translation. Instead of being at negative 3, we go to negative 1. We're just doing a translation. We're moving each mass 2 places to the right. And now, assuming that putting the fulcrum here would in fact put it in equilibrium, just moving the masses to the right, or in a different problem, moving it to the left, would make it it would put it in equilibrium state. That is, the moment would be 0. Okay. So let's look at that a little bit more closely. So in our case, we added 2 to each x value. Wherever the mass was, we added a constant. We could have taken away a constant. So if the moment is the summation of mi times xi, as I goes from 1 to some number. Well, if I translate each distance to the right, say 2 units or k units, let's call it x bar. Well, what's going to happen is, instead of x sub I, I'm going to have x sub I minus x bar. And now, it's in equilibrium. It's going to be 0. But let's work on the right side. We can distribute this. So this is the summation of mi xi minus mi x bar. And we know it still equals 0. Now, summation is friendly. When you have a subtraction, you can do the sum of this piece minus the sum of that piece. That is the sum of mi xi minus the sum of mi x bar is 0. And I'm really, really big on a subtraction equaling 0. If this minus this is 0, then they're equal to one another. The summation of mi xi is equal to the summation of mi x bar. Now, if you think about it, x bar is our number. You moved it 5 units to the right. That's why you wrote xi minus 5, x bar. X bar is a constant. You could factor it out in front. You can put this x bar in front. You know, if you have m1 x bar plus m2 x bar plus m3 times x bar, which is the same as the summation of xi times, I meant to say mi x bar, you could factor out the x bar, and then you get x bar times m1 plus m1, not mi, plus m2 plus m3. Now, what's in that bracket I can write as a summation. It's the summation of mi. And like I said, this x bar can come in front. Okay. Now, I want to solve for x bar. I want to know how much I should translate it. That is, where's the center? Remember, normally we center it at 0. But now I'm translating it over by x bar. So I kind of ran out of room, but basically, you divide both sides by the summation of mi. And what you get is this. Now this cancels. This is x bar. That is, x bar is nothing more than the summation of mi xi, all divided by the sum of the masses, the sum of mi. So that is where you should put, that's the center. That's where you should put the fulcrum. Let me be more clear. So x bar should be the summation of mi xi all over the sum of the masses. That would be the center. That would be the center. If you had a bar or a piece of wood like on a seesaw, and you put different weights on this board, we can figure out where to put the fulcrum. In other words, if we have a number line, man, right now you get to put 0 wherever you want. You have a number line, you put 0 wherever you want. And at -5, you have our mass of 6 kgs, and at 1, you have a smaller mass of 3 kgs, and at 3, you have a little bit bigger, it's 5. What is X bar? That is, where should you put the fulcrum? Well, it's a division. You have to figure out what the numerator is by doing this. You figure out what the bottom is. Well, the bottom is easy. It's 6 plus 3 plus 5. And then you just multiply. You get -30 plus. You multiply. You get 3 more plus. You multiply. You get 15. 3 times 5. Let me continue down here. 6 times -5 plus 1 times 3 plus 3 times 5 is 15. In the bottom you have 6 plus 3 plus 5. -30 plus 15 is -15. You add 3, you owe less. Instead of owing 15, now you owe 12. And the bottom is 14. You divide the top by 2 and the bottom by 2. That's where you should put the fulcrum to have equilibrium. If you put the fulcrum right at -6/7, the board would balance. The board would balance. Okay, the board would balance. Let's try another one like that. This is pretty neat. You want to know where to put the fulcrum so it balances. I mean, let's really suppose that this is real life stuff. You have this board, and for whatever reason, say you have this number line. Don't ask me why you have the number line on the board, but for argument's sake, here's 0. And you are going to put a weight or a box at 7. You're going to put another box at 8. And you need to put another box at 12. And one more box at 15. Just the way it is. You need to put these boxes. And the boxes, they're all weighed the same. Now, the question is, how do you support this board? Where would you put the fulcrum? Where would you put the fulcrum? Of course, if you put it over here, it's going to topple over. Because you have nothing to the left. You don't have anything out here. Where do you put the fulcrum? Okay, where do you support it? The answer is very simple. You use the formula on top. You multiply those numbers plus, you multiply those numbers plus, you multiply those numbers. Remember, the ones are the masses of the boxes. And lastly, you multiply those numbers. And x bar would be that divided by, now you add up the m's. 1 is m1, that 1 is m2, that 1 is m3, and that 1 is m4. And for the record, that's x1, x2 is 8, x sub 3 is 12, and the 15 is x4. You multiply the m's by the corresponding x's. And when you add up the 4 ones, of course you're going to get 4. So the bottom is 4. 7 plus 8 is 15, plus another 15 is 30, plus 12 more is 42. And you divide the top by 2, you divide the bottom by 2. You get 21 over 2, which is 10.5. 10 and a half. It's 10 and 1/2. What does that mean for us? Well, 10's right in between 8 and 12. 8 and 12. So right here, 10 and a half, you put the fulcrum. You really should have her support there. Now, does it have to look like a triangle? No. I mean, you can put a leg there. And, I'm not saying you don't have to put other legs, but you really should put one right at 10.5. You really should put one at 10.5. And unlike this last leg, all the legs, of course, should be the same height. Table legs. And that's the best way to support this board. Now, one last comment I want to say. We did not, and nor will we did not take into account the weight of the board. That's beyond the scope of these problems. We did not take into account the weight of the board. Okay? We did not. Of course, if we had this problem, and we only take into account the weight of the objects we put on the board, if we have this board that is extremely long, it is extremely long, and we put an object here, and an object here, and an object here, and another object here and here, and say they all weigh the same, and they're all equally spread out. That is, if this is 0 right here, they're all equally spread out, and they weigh the same. It's reasonable to put the fulcrum there. But that's not going to work because the board has weight, and it's going to topple over. Okay. But for these problems, we're talking about as if the board has no weight at all. Absolutely no weight. Which is a problem that I used to have as a student with physics problems, because this is physics. And the reason I had problems is because they were never correct. That is, if you put the fulcrum in this last example where I said, the table would topple over. Okay. Now, what if we are in 2D and we want the moments of the center of mass? We have these formulas. And it's just what we did. The moment about the y-axis, which is denoted m sub y, is just sum up the mi times the xi's. And the moments about the x-axis, denoted m sub x, is just the summation of mi times yi. This is purely definition. Really nothing to understand. Now, so again, we are now in 2D, not just on a linear line. We're in 2D. The center of mass, which is also the center of gravity, is given by, well, it's going to be some point. What's the center of mass? It's going to be given by x bar, which is the summation of the mixi's divided by the summation of the mi's, just like we did in linear. And then we do it again for the second dimension. It's the summation of the mi's times the y component, the y position, divided by the sum of the masses. Now, let's see. This numerator right here, if you want to be fancy, it's the same as this, and it's called my. So in your textbook, it's going to say x bar is m sub y over the summation of mi. Whenever you see the summation of mi-yi, you can call it mx. So right here, this is m sub x. And when you divide it by the summation of the summation of mi, you get y bar. And x bar, comma y bar, that's the center of mass, the center of gravity. In theory, and I still have problems with this, but in theory, if you go to the center of gravity, you can lift some very heavy weight, way more than the strongest weightlifter. You can probably lift it with your finger. Okay. So suppose you have some masses at these given positions. You have a mass, and they are at some point xy. The first mass is 2 kilograms, and it's at the origin, for example. And say the second mass is, 1 kilogram. It's at negative 1, 2. And the next one is 6 kilograms, and it's at 3, negative 1. The next one, 3 kgs, it's at 2, 2. And the next one and last one, 2 kgs, and it's at 0, 1. So I'm not going to draw all of this, but at this point here, at 0, 0, we have a box. Now, a box is just at a point. We're going to think of a box being just a point. And that box weighs 2 kilograms. And at negative 1, 2, right here, we have another object. It's 1 kilogram. And then at 3, negative 1, we have yet another box or another weight, 6 kilograms. And the question is, what's the center of mass? In other words, you have a table. Again, we're not going to talk about the weight of the table. Now, you go underneath the table, and again, the table has these handful of weights. You have a weight at 2, 2. You have another weight at 0, 1. You have 6 weights, 5 weights. Those 5 weights. And you want to lift this table. Well, if you just using your hand, you put your hand there and you try to lift it, it's not going to happen. It's not going to happen. Likewise, if you put your hand here, you're not going to be able to lift it. I mean, you're just going to lift that end, and this end over here won't move. Okay, so, basically you have to put your hand elsewhere. Again, you may say, well, put it at the center. Well, that's not true. If this is a table and you have a 100-pound weight right there, you try lifting the table by putting your hand in the center. It's not going to happen. It's not going to happen. You're going to have to put your hand more here. Okay. So the question is, where is the center of mass? Again, we're not talking about the weight of the table at all. Make believe the table only weighs 0.0000000000001 kgs. It's insignificant. Well, to find x bar is the summation of the masses times the x values divided by the sum of the masses. So I multiply 2 by the x value, the mass times the x value. I multiply the next mass by the x value. Remember, x value, y value. Multiply the 6 by the x value. 6 times 3. Plus, the 3 gets multiplied by the 2. Plus, the 2 gets multiplied by the 0. And I divide this by the sum of the masses. 2 plus 1 plus 6 plus 3 plus 2. 2 plus 1 plus 6 plus 3 plus 2. And for the bottom, I get 6, 8, 9, 11, 14. For the top, I get 0, negative 1, plus 18, that's 17, plus 6, that's 23, plus this is 0. I get 23 over 14. That's the x value of the center. That's x bar, excuse me. Now, we also want to find y bar. It's the same thing. It's the summation of the masses times the y value where it's located, divided by the summation of the masses. Well, we just add up the mi's, we got 14. Now we're going to do the same thing that we did for the numerator, except for the y values. I'm going to multiply 2 times 0, plus 1 times 2, plus 6 times negative 1, plus 3 times 2, plus 2 times 1. And for the numerator, I get 0 plus 2 is 2. Now, this is negative 6 plus 6, so that cancels out. So I still have the 2 from those 2. 2 plus 2, this last 2 is also 2. 2 plus 2 is 4. You get 4 over 14, which reduces to 2 over 7. So right here in the middle, I'm sorry I ran out of room, but the center of mass would be at x bar, comma, y bar. But we just calculated this. X bar is 23 over 14. Y bar, 2 over 7. That's the center of mass. If the table was weightless, you can go to this point and you can lift it with your finger. Now, I suspect the reason that you really can't lift it with your finger is because if this is the grid your finger is maybe the contact that your finger has with the table is that amount. That's not 1 point. Okay, that's not 1 point. I agree that we've always listed this or wrote this or represented that as 1 point. But that's way, way bigger than 1 point. A point is much finer. It's finer than what's inside that circle. It's even finer than, see if I can draw, it's even finer than that. A point is infinitely small. So I guess if your finger, or you can find the pencil tip that is, the tip is infinitely small. Smaller and smaller and smaller, you can lift the table. And you know what? That very, very thin point on the pencil can easily be broken, but the table won't break it because you went to the center of mass. But it would break because you can get that pencil tip to be small enough. Okay, or nobody can actually go to an X and Y axis. Nobody can go to an X and Y axis and put a point down. Because if I blow this up, you know, that's not a point. You can't say, come on, that's at 2, 1. No, it's not. No, it's not. That's absurd to say that point is at 2, 1. Why? Because how do you know it's not at 2.1.98? How do you know it's not there? Because this point is actually many points. It's many points. Okay, but if you can actually go to the pointer center, you can lift a 10,000-pound weight. If you can go to the center of mass, weight, okay. That completes this section. Work on these problems, you can do it.